So hello, everybody. I am Andrew Godwin, and I'm here to talk about channels. But first of all, a bit about who I am. So I'm a senior software engineer at Eventbrite just down the road, and I used to work on migrations and South as part of Django, which was a good 8 or so years of my life in Django, and the reason I'm a core developer on Django in the first place. But what this talk about is a new thing called channels. So channels has been out for about 1.5 years now. It's a relatively new thing in the Django world. And what it is, or rather the headline feature, is about WebSockets. But this talk is to explain like what underlies channels, what it really means, and like what's actually going on underneath there and what you want to be doing. So first of all, channels, as I said, was born from the idea of Django does not have support for WebSockets. WebSockets have come along, I think they're about 4 or 5 years old now. I've been working with them and since that time. I've been doing stuff like in Eventlet and G-Event for a while. But Django, as a first-class web framework, did not have support for them, as most Django frameworks did not have support for WebSockets. And so part of this was, well, OK, how do we take Django and bring it forward to have support for WebSockets? But also, as part of that process, and as I'll explain here, it took me on a much longer journey that comes to a solution that is a bit more generic and a bit more wide-ranging to the solution of, well, how does Python do concurrency in general? And we'll look at that later. But the crux of all this is that there is underlying the idea of, well, what if Django supports WebSockets, the thing I call the real hard problem. And it is not what seems like the initial problem, of which we'll come to in a second, of, well, WSGI doesn't support WebSockets. What the real hard problem is coordinating things asynchronously across a system. And as we'll see in a bit, this is not just about literally talking the WebSocket protocol to a browser, but more about like when one designs a system that includes WebSockets, what do you want? Like, why are you including them? What is the purpose of them? What are the reasons you're including them? And if you look closely at WebSockets, not just as a protocol, but as a way of designing sites and systems, you come across a different set of problems, all to do with coordination, that are much more difficult than the basic one. But let's go to the basic one first. So the basic problem that Python has had for a very long time, and the reason it doesn't really have good WebSocket support, is WSGI. Now, I love WSGI. It's a great format protocol, and it's very simple. At its core, it's this guarantee. You take a request, and you return a response. It's pretty simple. You write a callable. The callable takes an environ dictionary and another callable to return headers, and then you just return what you want to send back. Anyone can write one. It's been around for a very long time. It's very compatible. It has some quirks around encoding, but we all kind of understand what's going on there pretty much. And if you take this thing and map it to HTTP1, it maps really well, because that's what it was designed for. WSGI comes from CGI. CGI is its sort of, its ancestor in a way. And so the way it works is very similar to CGI. You have a process that you send a request to, and then the request gets handled, it sends back a response. And the same process can handle as multiple requests and responses pretty easily, or you can call one process each time. But the same calling pattern works really well for this kind of layout. And even in today's modern new world of HTTP2, we can still have the same kind of pattern. So for those of you who don't know, HTTP2 has many new features. But one of the key ones is that you can interleave multiple requests and responses on the same connection. So as the diagram here shows, you can have more than one request in flight at once, and the responses can come back out of order even if you want them to as well. Now, what we can just do here with WSGI is just take those requests, split them off to different processes, and just handle them separately, because HTTP is a stateless protocol. Any HTTP request can be handled by any server. We don't have to care about what one handles it. So even though there's more than one over the same connection, this is really the same layout as, well, what if there are 4 connections with 1 request each? We handle them the same way. So for this part of H2 at least, we don't have to care too much about what's going on. But then we get to WebSockets. WebSockets are an open, bidirectional, like there's no control about who sends and receives at any given time protocol. And the idea is the browser opens a connection, and then the server or the browser can send anything at any time over the socket. There is no request-response pattern. You can just send forever. You can just receive forever. You can wait for 3 hours between each send. And so you come with a lot of problems here around, well, how do we structure Python to handle this? So in particular, imagine a single Python process handling WebSocket. Like, because of the way it works, it has to sit there open for a while and sort of go, well, OK, we have to sort of have a process open that just handles this one socket. We can't have that process handle anything else. If there's a 2-hour gap between the next receive, the process has to sit there waiting for the next receive to happen. And so given that, we have to have one process per socket. And this also has a problem with WSGI in that it doesn't map to that abstraction I showed you a few slides ago. Like, you can no longer have a piece of code that's callable that takes a request and returns a response. There is no request and response in this paradigm. We can't do that anymore. And so the question really becomes, well, how do we handle that problem of taking a WebSocket connection and mapping it into Python? And that's the place I started out with this project. It's like, OK, we have a WebSocket connection. We want to take it and handle it in Python efficiently so we have more than one process per connection, because if we had to have one Python process per connection, well, that's just terrible for performance, obviously. And so this comes to the basic design of channels. And so let's look at how you might handle this in a simplistic case. So let's say you take asyncio or eventlet or gevent, one of the many, twisted even, one of the many solutions you have for doing threading inside of Python without using the pretty badly performing main threading module. Like, if you use main threading, it's pretty poor performance. 3 or 4 threads maximum before it gets really bad. So these other ones can do thousands of things concurrently. It works pretty well. But what we'll do, we'll naively do one server. We'll go, OK, we'll have one server. It has, so let's say, asyncio. It decodes all the stuff and goes, OK, I am going to handle all these sockets, and when somebody sends a message in, so say I'm a chat room in this case, someone's going to send in a message, and I'm going to send it out to everybody else in the chat room. Pretty simple. This is actually quite easy to write in a few hours if you have the right libraries, and there are good libraries for this stuff. Now, let's say that our chat is successful, because we want it to be, because we have ambitions, and we go to 2 servers. Now, with WSGI, we would just fire up a second server, and because HTTP is stateless, we're like, OK, that's fine. We can just load balance the requests across different servers. Nobody cares very much. However, with WebSockets, you have a couple of problems. So first of all, the connections are long running, and we can still load balance. That's fine. We can still have different servers and load balance connections across based on how many are open still on the other server. The problem we have is when we look at our chat solution now, where a client sends a message to the server it's talking to, but people are connected to the chat room from all different sorts of servers. So we have to basically take that message and somehow get it to all the servers in our cluster. Imagine there's more than 2. Imagine there's like 20 of these. How do we breach this gap? And that's what I'm talking about here is the real hard problem. And this is the sort of thing that Django and Channels actually solves for you. Like, when I was looking at this, I could write the simple version of this very quickly. But when trying to write examples and practical like case studies, it's this problem that really comes. You go, oh, anything we do with WebSockets is naturally going to be broadcast-based or event-based. And how do we have events go across the entirety of a Django system? And that's broadcast is the underlying thing that Channels is looking at. And it's kind of a difficult problem, because if you think about it, what we're having to do is coordinate what's happening on different servers, potentially in different racks or different data centers to each other, hopefully in the same rack at least. And what Channels kind of became then is its foundation for running this kind of framework or this kind of system at scale. What underlies Channels is a way to not just solve the problem of WebSockets, but to also solve the problem of, well, how do we do this for chat? How do we do this for IRC? How do we do this for email? And many other things that require sort of knowing about events from all different places in the system. And naturally, I can't just claim that Channels solves this problem, because architecture is about trade-offs. And if you want things to happen throughout a system globally, you're going to have to give something up. And we'll see what those are in a second. So here are some examples of trade-offs that I would have to make. If you're designing a task queue-ish worker system like Channels is based on, these are some of your sort of 4 basic constraints you would have to have in that task queue. Do you deliver messages between systems at most once, meaning that if you fail, a message isn't delivered? Or do you deliver at least once, meaning if you fail, a message is delivered twice or 3 times? You can't choose exactly once, because this is distributed systems. You have to choose one of the 2 bad options. Similarly, do you want the message to be ordered or unordered? There's different trade-offs in each scenario. Do you want the queue to be first in, first out, as in traditional queue, or first in, last out, as in it's a stack? Do you want messages to expire or persist forever so you can handle them? And all of these questions, each side of the decisions comes with some pros and some cons. And part of the difficulty in designing the system is that not only do I have to pick a set of these that we encode into the design of channels, but also you as developers have to match pretty closely with this, otherwise you won't find it useful for yourselves. And I'll say right up now, channels does not apply to every situation because it has to be opinionated in this stance. But my hope is the design is at least approximately applicable to all of the different, a common set of problems. So let's look at some of the things that I am envisaging when I'm thinking about, a year ago, going, Andrew, what are people going to use channels for? Why am I designing this? So obviously, number one, WebSockets. We all love them, apparently. Number two, one of the problems we have at Eventbrite a lot is service-oriented architecture, which, again, if you haven't seen it, is where you write things as different services on different machines, and you communicate between them. So you might say, well, to render this page, we talk to the service that's about events, and that talks to the service that's about tickets, and that gets the prices from there and gets the prices back. And even that is a communication system that requires some kind of cross-server messaging. So as we'll see in a bit, channels can be used for that as well. But as I said before, chat and email integrations as well. Chat is a very important thing where obviously it's broadcast-based. If you have like chatbots at IRC, you need a system that works in real time, like WebSockets, where you can send and receive whenever you want. And then finally, other protocols. In particular, the Internet of Things is full of a lot of protocols of things just connect and send you stuff in small binary packets, or you send them stuff in binary packets, and it's not HTTP. And so these are sort of the areas that Channels is aiming at to be like, well, it's stretching, and it doesn't give you full-fledged support for all these, but it's a foundation you can build on top of for this kind of stuff. But let's look at what makes it hard. And as I said before, the only reason it's hard is because it's a distributed system. Now, if you haven't been doing software architecture very long, first of all, congratulations. It's a very, very depressing thing to be happening. But the second thing is you quickly learn that when somebody tells you a system is distributed, you immediately hang your head and go, oh, because there is no way of doing a perfect distributed system. I'm sure some of you have heard of the CAP theorem. Hands up, who's heard of the CAP theorem? A few of you? Okay, about a third of the room. I'll describe it for everybody else. So the CAP theorem is the idea there are three properties of a distributed system. There's consistency, availability, and partition tolerance. And you can have at most two of them. It's one of those traditional, like, do you want it fast, cheap, or nice? Pick any two kind of situations. And so the idea is you can have a system that's consistent and always available, but it won't deal with partitions very well. You can have a system that's available and deals with partitions, but the data won't be consistent. So as an example, take Cassandra or React. These are systems that deal well with partitions because they rejoin and do things very well, and they're always available. You can always ask them questions, but they're not consistent. If you ask different nodes in the ring the same question, you'll get different answers back. A traditional database like Postgres or MySQL is consistent, but it's not always available, or it's not partition tolerant. You get to choose a little bit of that in the replication setup. But the idea is you have to choose those kind of trade-offs. And the same thing happens to channels. We have to choose trade-offs. And a lot of design channels is based on that kind of choice. And where do these trade-offs come from? Well, if you model systems and networks in a lovely lab with white walls, everyone's wearing coats, there's lovely tea and coffee on the wall, it's fine. But in the real world, we have real engineering problems. And this is things like connections are very stateful, and networks are also very unreliable. If you've ever written any networking code, you'll know the network is your worst enemy. You should never trust it, and it will do everything in its power to make your things fail. There's also things like bottlenecks and machines dying. Like you have to design a system where, like, imagine a cloud of servers and the Netflix chaos monkeys running around, unplugging them and rewiring them. And crucially, the one I love telling junior engineers is it might be up, but 3 seconds slow. Like the latency is and they're like, ooh, because their systems, like system designs, often deal well with machines that are definitely up or definitely down, but machines that are very slow tend to perform really badly in a lot of common designs. So like, well, the machine's technically there, but if you send it any queries, it takes like 9 seconds to reply, and your whole system gets dragged down as a result. So there's a lot of like very nasty like subtleties to this kind of design you really have to focus on. So what is the design that Channels has? So in its base form, it is a message bus. I'm sure you've seen or heard of message buses. There are some things called enterprise message buses that they're enterprise because they're slow. It's great. But the idea is it is a central bus which anything can read or write from. In particular, these 5 things at the top here are your 5 primitives that channels gives you for what you can do. You can send to a channel, you can receive from a channel, and channels are just queues with names, and the names are just strings. So for example, you can make up your own channel name and send to it if you want to. And then on top of channels, you have groups, and groups are merely groups of channels, and you can add channels to a group, you can remove channels from a group, and you can send to a group, and sending to a group sends onto all the channels inside it. Crucially, you cannot do things like what channels are in this group, or is this channel connected? Because those are questions that, if you try and answer them, the complexity of distributed systems means it gets harder and harder to answer questions. In particular, answering the question, is the channel connected, is very difficult. Like, how do you even break that across the gap to talk to the server that has the other end to get it back in a way that you can rely on? And the idea is all of these 5 questions can be asked by anything, and what they are mapped onto is a thing called ASGI, which is similar to WSGI in a way. But the idea is it is a common way to both send messages to and from Python applications, and also a way of encoding HTTP and WebSocket onto those connections. So much like WSGI tells you, okay, this is how a request comes in a dictionary format, ASGI says, well, this is how a request comes in as messages, or this is how a WebSocket comes in as messages. And it's all based on like JSON-ish dictionaries and easy to understand. But that's the basic idea. And what happens is it's pluggable, because Django's best thing about Django is that you can take Django, and if you want to, just remove part of it and put your own thing in. Like, one of the things I came to Django for is that Django doesn't get in your way when you have a complex problem, and it doesn't know how to solve it. Like, we are under no illusion that Django will solve everyone's problems. Our goal is to give you a good framework to start with, and then as you grow, gracefully fall away and leave you with a good design pattern and a good place to put your own code. And so the idea here is that ASGI is very similar. It has a default implementation that uses Redis as a backend, but it's a pluggable interface. You just have to implement these 5 methods. And so we ship with the Redis one. We ship with one that works using shared memory segments in POSIX, which is slightly, shall we say, dark magic, but it works reasonably well. Just don't look at the documentation for POSIX IPC stuff. And like, so this one works across a network. And in fact, it does sharding across Redis too. So if you have a big network, you can shard onto multiple Redis servers entirely independently, and it scales pretty well horizontally with that kind of load. This is more for small installations. I am a big believer in scaling down as well as scaling up. And so if you have just one machine, you can just run the shared memory backend and then don't need to run a server. The things just talk to each other magically through the shared memory segments. But of course, I'm sure a lot of you looking at this thing and, well, Andrew, your diagram here shows all traffic on the entire site going through one part of it. That's called a bottleneck, and you're very right about this. And so one of the things we have in the design is the idea of, well, you can have a way where, because you have this very abstract, very low-level interface, you can be a bit more intelligent about how you route things. So in particular, Channels has a mode in the Redis layer where it can route things locally on the machine if it's serviceable on the machine, or if it knows it's going to a particular socket, it routes it across the network. So for example, when you're handling an incoming WebSocket message, any Django machine can handle the message and process it. Like the way Channels is written, it's like views, anything can handle the incoming message. When you send a response back, the response channel is tied to a particular TCP socket on the machine somewhere in your network. And so that one can't go on the local machine. It has to go across the network to find the right machine to then terminate on. And so the channel layer knows about this stuff, and it can intelligently route based on these things. And that's why you can get pretty decent performance between the two of them. So you can get decent performance on the same machine, because like if you run a thing that terminates sockets and Django on the same machine, it routes them locally. And when it has to go and do a broadcast, the broadcast then goes across the network. And if you're interested about this in a bit more detail, ASGI has a full specification written sort of in PEP style. It explains the exact guarantees and the way it's structured and the way it's designed. So if you are interested in how this stuff works, it is there for you to read. And comments and improvements are always welcome. The spec is always being refined slightly as we approach 1.0, but it's pretty much not nailed down at this point. And so what Channels does is it takes those low-level operations I just showed you, and it wraps them in a higher level. Because Channels' job is to be, it's the Django, it's a nicety to WSGI, the commonality. And so what channels gives you is things like handlers for WebSocket authentication. So for example, if you connect to Django with channels installed and you have a WebSocket, Django can just take the cookies on that request from the socket and decode the session and give you a user on a WebSocket. Like for free, you get the same authentication system you get everywhere else. It can give you things like good group management. It has data binding built in. So when you save a model in Django, it can send messages onto groups for you. So you say, okay, when someone connects, put them in the group that listens to model changes. And when a model changes, send it to that group. And then with a few small changes, you immediately have a solution where whenever somebody edits the admin and hits save, the web page can get a message and update. And what it's constructed of really is a lot of separate pieces. So like often I will describe channels as a single project, but channels is unusually for Django more than one monolithic code base. And we're trying to change and be a bit more modern. And so channels is really 5 things. There is channels, the actual package name, which is the Django integration layer. That's the bit that wraps the low-level interface and gives you things like authentication and sessions and all the niceties. There is Daphne. Daphne is a bit like Gunicorn. It is a HTTP server, but rather than speaking WSGI, it speaks ASGI. And so it's our reference server for, it can terminate HTTP, it can terminate WebSockets for you, and it will put those onto the system and let Django run this way. Crucially, you don't have to just run Daphne. You can run Daphne alongside uWSGI or Gunicorn if you want to. But if you want to service WebSockets, you have to run a server that can speak ASGI because WSGI doesn't do it. And so for now, it's just Daphne. I'm talking to some other servers to try, I had a good talk with both some people from ModWSGI and from Gunicorn recently, so hoping we get support in there natively as well pretty soon. And then once you've got those two ends of it, as you see, like the thing that connects to connections and the thing that actually talks to Django, the middle layer is ASGI, and those are those 3 packages. So there's an ASGI ref, just some common base libraries and standard functions. It's not very useful by itself. And then a Redis backend and a local memory and a sort of shared memory backend. And these are the 2 reference implementations again, but the idea is they're pluggable. We already have somebody trying to do one based on AMQP, which is tricky because AMQP is not built for low latency, but they're having a go. And we'll see how we get more of those in the future. And so what does channels provide? So I said it provides a lot of high-level stuff. So here's some of the high-level stuff. So not only do we have these nice sessions and auth stuff, but also there's a structure to how you write code. And so what channels does, and you'll see this later in a few slides, is it lets you write code for WebSockets like you write code for normal views in Django. You write simple functions. There's no threading concerns to worry about. You say, this function handles a connection. And the function gets a message saying, well, the connection's on this path, it's on this cookies. And then you just do things, and then you return. And these look like views, and they're called consumers. And Django gives you these consumers that act like views, gives you routing for them that acts like Django's normal URL routing. So you can say, well, if someone connects to the socket on this path, call this function. If someone connects on this path, call this function. And it also gives you sessions and authentication and other like, if you just run server with channels installed, run server in Django with channels just supports WebSockets natively. You just do run server, things just work. So that's all sort of built in for you, and that's pretty nice. So I've been theorizing for a while. Let's get actually concrete and let's show you some actual code because it's very important. So this is what those consumers look like. As I said, they're very similar to views. They are a thing that takes a message and can send other messages. It's sort of a superset of what views do. So here I've got a very basic chat, which is my favorite example, as I'm sure you've noticed. So channels works on events, and WebSockets have 3 kinds of events incoming. They have connection, they have the client sent you a frame, which is called receive, and they have disconnection. And there's one kind outgoing, which is I want to send you a frame. And so when someone connects, you get a connection message. And what you do in Django is say, OK, when we get a message on WebSocket.connect, call this function. And in this case, my function just adds that message's reply channel, as in the one that we send things to the browser on, to a group. When I receive a message, I then take the message they send me and then send it back onto the group. And I said before, when you send onto a group, you send onto all the channels connected to it. So what we're doing here really is we're sending to every connected socket, because that first call there adds them to the group. So we're sending to every single connected socket at once. And then finally, for a bit of cleanup, when someone disconnects, we remove them from the group. We don't have to. If you send to a channel that isn't listening, it just sort of expires after a while. But it's good for keeping the memory usage lower in Redis. And Django has some, and Channels has some cleanup stuff for you, but it's good to be like this. As I said, you then route them. Routing looks like URLs. You just say a routing.py, and you import route, and you make a list of things. This doesn't show the path matching, but you get URL path matching too. You can match on any part of the message. So, for example, you can match on method if you're doing requests, for example. And then finally, if you want to, you can ignore all that code and look at this code, which is the class-based version, which is much shorter. And so the class-based version, Channels has things like the common pattern of when you connect, you add to a group. When you disconnect, you remove from the group. It has built-in stuff for that. So you subclass a normal consumer we have already. You say connection groups is chat, and then Channels manages that connection stuff for you. And then you just write a receive handler the same way we did before. And then routing with classes is a lot easier because classes know what channels they want to listen to. So you just say root class, like let this class listen to whatever it wants. And you can have path restrictions there too. But the whole idea is that it's pretty well contained and pretty self-contained and works out pretty nicely. And if you're interested, there is a full worked example of this you can download and install with multiple chat rooms, authentication, many more features, a README, lots of comments. There is also a live blog and a data binding example, all in this Git repository. I'm a big believer in giving people options. So if you learn by looking at code, download the repository, step through it. There's some good instructions on how to install it, get it running, and you'll have a running chat in your browser in about 30 seconds. And it even comes with challenges. You want to it says why didn't you try doing this? It gives you some hints about how to do it. So try and learn by doing with channels. And it's quite a good way to. That's how I learn anyway. So that's quite good for me. But let's turn away from Django now. So this topic was titled, or the abstract included a thing about talking about what channels is outside of Django. And channels is not meant to be just a Django project. Like WSGI is not just for Django, and I see the same about channels. And in particular, in the broad sense, I would like to have a solution for WebSockets in Python in general, but this is not about that. This is about a different angle of, well, what is the thing that underlies channels useful for? And as I said earlier, there's many different uses. So here's a basic step through about how one would use channels outside of Django, because any Python script, 2 or 3, can just use channels. All you do is you take a channel layer on the command line or via a config file, but the idea is you take an object, which is a channel layer, and that has 5 methods on it for the 5 things from earlier, send, receive, and group add and group remove and stuff. So your thing just has to take a layer. It just has to then somehow have an event loop, either a while true loop or twisted or asyncio or something that basically lets it go around and listen for messages on these channels. Basically just call receive again and again if you're doing that kind of stuff. And then finally, you just call send and receive on it. And it's actually trivial to write a small piece of Python code that talks to Django or talks to anything else via channels. Because all you have is, like, you can ignore the groups if you want. You can just have send and receive primitives. If you just want to have a system that dispatches messages on a bus, just send onto the channel and then receive from it. And the way receive works is if you have 5 clients receiving off the same channel, each of them only gets one of the messages. It's like it is literally a task queue. So it's very good for that stuff. So let's look at a concrete example of what we're looking at inside Eventbrite for using this for, which is service-oriented architecture. So Eventbrite has our stuff spread up into separate services across the code base, and any given web page call calls a good number of them. And the old solution was a direct HTTP call from the code to a server running for that service. This has many problems. In particular, if you are doing nested calls, where so an event service calls a ticket service, calls a pricing service, then you have 3 nested HTTP calls. And in addition, if you want to run multiple HTTP calls in parallel, you can't do that in core Python. And unfortunately, Eventbrite's code is old enough that we can't easily add in asyncio or gevent or anything like that. We have to have this stuff either be synchronous or bust. And so what the nice thing here is that what we can do is we can just call send. We can send on different channels with different services, and then just sit there and block on receive synchronously. And because Redis is doing all the asynchronous lifting for us, we can have exactly synchronous code that just handles multiple calls in parallel. And moreover, because these things are on a bus, there's no need to configure the services or configure all our web servers. Like, well, here are the addresses of all the different services you want to talk to. Make sure the firewall ports are open. Our security people having a nightmare of time. Like, well, why are there 25 different ports open? Well, there's 25 services. Instead, you have a single bus you can talk to, and then you can add and remove things from the bus, and it scales much more efficiently in that sense as well. And so the idea here is to have this sort of overarching thing where rather than Django being a single process tied into WSGI, you can build systems around it. And like as I've gone through my career in the last decade or so, what I found is a lot of complex sites are much more systems than they are single code bases. And what I think Django's been missing for a long time, and the things WebSockets really highlighted, is there is no way to easily build a system of components. Like we have Celery, and Celery is very good for some stuff, but it doesn't solve the general problem of doing socket handling at scale. And so what Channels tries to provide is this way of running, well, you can run WebSockets, but also you can run things like email, IRC, and then you can run Django as worker processes. And because it's one system, there is a standard to build around, which is very important. Like Django's job as a framework is to be semi-opinionated. Like if we just told you, do whatever you like, it wouldn't be a very good framework. Like the idea is to give you some reasonable, like basic defaults. And then also to let things fall away. And the idea is like designing a message passing system. It's a very common design pattern in distributed systems. It's well understood. We know the limitations. We know the way to scale it. And so encouraging you to build things like this is not bad, because when you get to the point of we need to make this more efficient, or like we have specific problem X, there's a lot of like research and case studies about like how to scale this kind of system. And in general, a lot of systems are built like this at scale as well. Like message passing is a very common way of doing this stuff. There's even proof sets for this kind of languages. And so the idea there is to give you the sort of structure of building WebSockets, but also more stuff in one big go. And this is very much the idea, like Channels is a tool for you to use to build more complex systems. And so rather than just saying, hey, here's a thing that just does WebSockets, the idea is, well, when WebRTC comes along in 2 years, the same abstraction works for WebRTC, right? When something else comes along in a few years, the same abstraction works for that. The idea is building for the future rather than building for the present. Like what can we do to Django and to Python in general that lets it be suitable for handling these sort of big problems of we have, thousands or hundreds of thousands of clients connecting at once with stateful connections, requesting things, sending things back. Even things like game servers, you can do things like this for that kind of stuff. And with Channels, there is more to be done. It is not at 1.0 yet, but 1.0 is very close. It is still a third-party package, but soon it will be officially under Django as an organization. That's happening as soon as the technical board election finishes, hopefully. And then what we'll have an official Django package that is Channels. It's not going to be part of core, but it'll be on our documentation. You'll be able to install it. We'll have our security policy in place for it. We'll have all the sort of stuff you expect from Django, like good release notes, backwards into backward changes, that kind of stuff. And it will continue to develop at a faster pace than Django. And one day we may merge in with Django Core. 1.11, the next release of Django, is an LTS, so probably not then, but maybe 2.0 after that. We'll see. But this is, there's still more to be done. And thankfully, Mozilla have been very generous and gave us $150,000 to fund development of our Channels, and we've used about half of that so far. But there is more work to be done. We have a list of tasks. We have funding to pay you for those tasks if you are a freelancer and wish to be paid. And if you don't wish to be paid, that's fine as well. But if you are interested, please come and talk to me or go to the website, and there's more about that stuff too. And as I said at the beginning, Channels makes trade-offs. The trade-offs may not be for you. And particularly, we're at PyBay. We're in Silicon Valley, essentially. There are probably people in this room whose companies are so big that they are so specialized that this makes no sense to them at all. Like if, I'm sure some of you read the Uber Postgres and MySQL article, right? Like when you are that specialized and that big, like things like the way that indexes work become really important to you. And so Channels is for the 95% of the rest of us. Well, not the rest of us, Eventbrite specialty, but like it's for the 95% of people who like, it's a good common pattern you can build upon for a medium-sized company. And then when you get very specialized, it's a sort of thing where like you won't go, damn it, we built it really badly. Like, okay, it's not gonna be perfect, but it's a good base to build from. And that's the idea here. That's the idea of Channels here. But if you are from a big company and want to drop this in for a feature, if it matches your trade-offs, good luck, but you'll know more than I do about this kind of stuff. And finally, like, I want to put this in perspective of what Django has been. So Django was released in 2005. And we look at the progression of what happens on the web or in technology. Like in 1995, websites weren't really, the internet existed, web existed. But like if you were a software company, you probably made desktop applications. You probably made things, shipped them on floppies or CDs. I get my timescales there. Maybe authentication dongles if you're super fancy. And then step forward 10 years, and now if you're a software company, you're probably a website. You're probably one of the big websites of the noughties. And then step back to around now. Like these days, what are big companies? Well, they're apps as well. They're rich websites. They're much more difficult experiences. And Django was built in 2005. And Django was built in the era of static HTML and rendering requests, and HTTP requests are enough. And there's a fantastic framework for that. But what I'm trying to do here is like, well, what is the job of Django as a framework? Is our job to fulfill that exact original design pattern? Or is our job to evolve with what Python has to evolve with as well, with like the wider tech community? Like as we progress, like what is 10 years from now? Like what are we going to be programming against? And like part of my goal here is to take Django and Python into that sort of brave new future of, well, what's coming next? Like it's not just the web. How do we deal with which websites? How do we interact with things like React properly? Like how do we do data binding? How do we do all this stuff properly? And like really my question there is like, what are the goals of Django? Like, do we adapt? Is Django done? Should we say Django is a great web framework for professional deadlines? We've done it. Everyone, congratulations. Walk off, leave it be. It's well done. I don't believe that, and I think we have to keep adapting to the changing web and that kind of thing. And that's kind of part of what my pitch of Channels is. And so I hope you've learned something. I hope you understand at least some of the challenges that are involved, and we have some time for questions. So thank you very much.
Do we have any questions? Cool.
Hi, thanks. That was really great. You talked a lot about trade-offs and the importance of trade-offs, and especially the importance of trade-offs in distributed systems. And you talked a little bit about some of the ideas and use cases that channels are designed to support well. Can you speak a little bit about other use cases that you think channels is not maybe a good fit for, or things that you considered but decided weren't as important as the other use cases you were considering?
That's a great question. So one of the things I'm considering is what already exists that's good. So for example, guaranteed, so channels is non-guaranteed delivery, it's at most once delivery. If you want guaranteed delivery, we have Celery for that. And so for example, channels is not good for doing things like financial transactions where things have to happen. Like if you want guaranteed delivery or like transactional emails, like, you know, or invoices being emailed, like that's not a good fit for channels, right? Because like those are things that must happen, and you'd much rather have somebody be sent 2 invoices than no invoices, for example. And so that's the trade-off as an example like that. I think at most once versus at least once is one of the major trade-offs we have. Other examples, let's think. So I was talking to Armin earlier, or yesterday in fact, about one of the other trade-offs. Like Channels has no way to see who is connected into a group, and so it doesn't have a support for presence promote. It's like if you want to do a presence-based application, you can do it on top of Channels, but we don't give you the logic, because like that's less a trade-off and more we didn't preach that question. But the idea, if you want to do presence, so like, you know, this person is in the chat room, you have to write a thing like, oh, it pings the server every 5 seconds and it keeps a liveliness check and expires it with a scheduled task that goes through every 30 seconds. There's a lot of logic there and a lot of specificity. That's something that we didn't put in rather than trading off the other way.
Is anybody doing multiple language interaction with channels right now, or with ASGI?
So multiple languages is interesting because the interface is a Python interface. It is an object you call methods on. So you could, in theory, call it from other languages, like, but you have to pick a particular backend. And so, for example, the Redis backend uses, you know, lpush and lpop with expiring key. Like, it's a certain way it uses keys in the database. I have been looking at potential ways to expose the Python interface through to a C level binding, but right now I'm much more focusing on getting it more use inside Python and inside other frameworks than sort of outside of Python in general. But, you know, it's theoretically possible, but and there are other languages. For example, there are some very old message passing solutions for this kind of stuff, like from like the parallel processing computers have like a crazy C-level based one as well. But there's no general good one because this is not a general solution. And maybe one day we'll have one, but that binding Python out to stuff is very, very difficult. Much harder than like CFFI for binding in. Oh, one more back.
So you mentioned that the ASGI is written as a PEP. It's written as a PEP, And
no, it's not a PEP. It is like a PEP.
it's like a
crucially,
PEP, right?
yes.
But I was going to ask, since WSGI is official PEP and there is even a WSGI module in Python, do you intend to actually submit it as a PEP and write the module that would go into Python for that?
So my intention is to get consensus first. A PEP is no good a PEP is no good as a way as a hammer to make people implement things. A PEP is good for solidifying consensus in a community, right? The PEP is just like, oh, we're all doing this, let's put it down officially. And so my goal is much more to reach out to other frameworks and to agree on stuff and to prove this in production first. And if it does prove well and everyone likes it, then come back and take that proto-PEP, polish it into a PEP with the help of people I know who've gone through the process before, and then officially turn to Python as a core and say, do we think this is a thing that's worth putting into Python? But the reason, like, it's written as a PEP because that's a very useful way, and we understand as developers how to read them. But my intention is right now, not a PEP right now. Like, I want consensus and proof first, then I will go for having it officially approved. Cool.
Anybody else? Going once, going twice.
Sold.
All right. Thanks, Andrew.
Thank you.